All right, our next example problem here, next problem for our problem sheet, involves an object hitting a wall and then bouncing back. I know in the problem I mentioned a person and then a car. There's a reason I end up switching them, but I made the mistake and I didn't actually change it from a person to a car. But it doesn't really matter. We just have a mass hitting the wall and bouncing back. So I think it's important to draw a picture every time you do one of these problems. I know that I've said before that you don't have to draw a picture, but I really do think it would help. So if we were to draw a picture of a wall and a mass going in at 12 meters per second, and then it rebounds with a velocity of 5.3 meters per second, we could see that the one should be positive and the other one should be negative. It doesn't say that in the problem, but you have to read the problem to understand that it rebounds, meaning it bounces back. This is where the tricky part, I guess, lies in the problem, and that's where most people made a mistake. So it wants to know how long the car, the ball, the person is in contact with the wall. So that's the equation we use because we have force, we have time, we have momentum. We're solving for the time. And we could plug in our momentum, but it's a little bit tricky, right? Because it doesn't just tell us what it is. It's going to be m vf minus vi. And if you remember, that's what change in momentum equals. We're going to put in our values. Check here what the mass was. 1,600 kilograms. Our final velocity was negative 5.2 minus the initial, which was 12.0. If you notice, if you take a negative 5.2 minus 12, you get something larger. Right? It's a lot more damage if you hit something and bounce back than it is if you just hit it and stop. And then our force was 1,900 newtons. Okay. Now we should realize too that the force is actually in that direction, and it should be a negative, at least in the picture that we have. Depending on the picture, if you draw the picture over here and the ball hitting it and going that way, that would change some things about it, but the values in the end would be the same. It would just change signs. So let's solve for the time. You'll notice that we should get a negative on the top and on the bottom. So we have 1,600 times negative 5.2 minus 12 divided by 9100. We should get a time of 3 seconds. It looks like for our significant digits, significant figures, it would be 3.0 seconds. Now you may ask, wow, 3 seconds? If a car hits a wall and lasts on the wall for 3 seconds, 1, 2, 3. Is that a long time? Yes. Yeah. The numbers in the problem were probably a little bit off from what they should have been, but this would be the time that we get based on these numbers. All right? So let's take a look now, lastly, at the final problem. If we can find it. It says a pop can is dropped from a height of 1.2 meters and hits the floor. It gives you a time. And then it says if it takes 1,800 newtons to burst the can, will it burst upon hitting the ground? So the real question is, how much force was there when it hit the ground? And we're going to compare it to that number right there. So our real question is how much force? You know, since this is right, and we can write it right here. So we have Ft equals change in P. And we're solving for the force, so the force is equal to the change in P divided by the change in T. The one thing the problem does not give us is the velocity. But we know from last chapter we can look at the energies to find the velocity. So if our height is 1.2 meters, we can use the equation that we found, and I'm not going to derive it, but the velocity down here will be equal to square root of 2gh. Square root of 2 times gravity. We can get rid of that. If you remember, I'm always used to using 9.80 for a certain sea level. 9.81 meters per second squared times our height, which is 1.2 meters. We should then get a value of approximately 5. So 2 times 9.81 times 1.2 square root of my answer, and my velocity is 4.85 meters per second. And it's going down, and that's important that it's going down. We're going to assume that once it hits the ground, it stops. So if I make this equation a little bigger, VF minus VI divided by change in T, we're going to solve for F. So my mass is 50 grams, or 500 grams, sorry. Say it again. I have it down here as 0.500 grams. It should have been 0.500 kilograms. Okay. If it was a half a gram for a can of pop, that wouldn't make too much sense. I know in your papers that's okay. You get these really small values, and I didn't say it to your class. So let's put that in there for the mass. 0.500 kilograms, which is 500 grams. My final velocity would be 0 minus a negative 4.85. And then we're going to divide by 0.0400 seconds. This number is going to be a little different than yours because, like I said, you converted. So I would get a force of about 61. If we look at the significant figures, 2 would be acceptable. If we look at all of them, our 1.2 meters. We could have 2. If you put 3, I would understand that also. We'd have 61 newtons. So would it break? No. It would not burst because 1800 newtons is greater than 61 newtons. Okay, and that would be your real final answer right there. Next, we're going to look at the collision problems involving the conservation of momentum.